Welcome back. This is the South Dakota School of Mines and Technology Thermodynamics II homework number 5, which is activity. Okay. Number 4 asks you to show that the Van Laar activity model is thermodynamically consistent, which means this thing. Okay. Now remember that thermodynamically consistent and satisfying Gibbs-Duhem are somewhat separate. You use Gibbs-Duhem to get to here, but you can satisfy Gibbs-Duhem and not satisfy that guy. Now, why do we do this? Normally, you don't really need to do this, okay? You don't really need to verify a model as thermodynamically consistent because somebody else has already done it. It's more for if I have data for gamma 1 and I have data for gamma 2, I could numerically integrate this to see does it equal 0. It should equal 0 if I integrate this, so to speak. Okay, numerically. And so here we're just kind of going through the motions of doing it. Okay, just so you can see how a model is thermodynamically consistent. We did one in class, and you're gonna, here we're gonna do it one more time. Okay. Okay, so I also need what does natural log gamma 1 equal and what does natural log gamma 2 equal. Okay. Now your book likes to keep everything in terms of RT, whereas everybody else in the world likes to absorb RT into the constants. We're going to assume that we're like the rest of the world, okay? Because it's going to, if this was RT, I could say this is RT, and it's still the same thing because the RT gets pulled out and that's equal to 0. Okay, so let's just assume that I'm looking at the models in this way. Okay, and so I want this to be, well, okay, fine, we'll do RT. But we're going to plug in RT, natural log of gamma 1, gamma 2, so that I can just leave it like this and say x1, x2. Oh, we're looking at the gammas. We got A times B over ax1 plus bx2 quantity squared, and here we got b a over b a x1 plus bx2 quantity squared. Okay. And now we're just gonna do the math. Okay. So the first thing I do is I recognize what equation I need to use. And once I've done that, and then I want to do a log, log here. Okay, so I want to use log rules. Okay, so 0 to 1, I got RT natural log of gamma 1 minus RT natural log of gamma 2 dx1. Okay, now I can just kind of plug them in, and that's what I'm going to do. So I have 0 to 1, and I'm also going to kind of distribute this a little bit so I can have a common denominator here. Okay, and so I'm going to have AB squared minus A squared B all over AX1 plus BX2 quantity squared dx1. The next thing I want to do is I want to make sure all my x2s are x1s. Otherwise, I need to do some goofy integration by parts, which I really don't want to do. Okay? And so I do that. Okay? So 0 to 1. Well, that's all constant. So I'm just going to call that like delta AB. Okay, so that's going to be my delta AB, so to speak. I'm going to just pull that out. Okay. So I have delta AB from 0 to 1, and I'm not going to, I could, but I'm not going to just in case. Okay. So delta AB is equal to dx1 all over, and I got ax1 plus b minus bx1 quantity squared. All right, now we're getting somewhere. Okay. And then See, now I'm getting into a pickle. Okay. I got something that I need to do integration by parts. Okay. On a quiz, on a test, or whatever, I am typically going to give you whatever that integral is going to be. Okay. In some generic form. You know, the generic form in this case would be like du over, au plus b quantity squared. Okay. And then I'd have to do the math to figure that stuff out. And so if I look that up really quick in my calc book, give me a second while I do that. Okay, or I could go to Wolfram. You know, Wolfram's really nice. The reason why is I can, do this really, really, really quick. Well, at least I used to be able to. I guess they changed it. Okay. Let's see here. I want to integrate. Ax plus b to the -2. Okay, so if I do that, they change the interface. All right, sorry for that. So according to this, that is equal to 1 over a times a x plus au plus b. Okay. Now I need to figure out how does that translate to my thing. So that's what I would give you. I'd give you, this thing. Okay, well, I have to figure out what that translates to. Okay, so if I bring that over, I have delta AB all over A. A in this case is A minus B. So I've got A minus B times A x1 minus B x1. And then my B in this case is just B. Okay, so plus B. Okay. From 0 to 1. Alright. Well, now I just kind of plug things in. Okay, let's see what happens. Okay, so let's plug that in full. So we have equals AB squared minus A squared B all over A minus B. When I'm all said and done, that, whatever's in here should be equal to 0. So 1 over, let's see here, I have A times 1 minus B times 1 plus B. Okay, so I got 1 over A. Okay. Minus 1 over A times 0 minus B times 0 plus B, which is minus 1 over B. Oh, is that the same thing as that? Who knows? Or did they cancel out each other, so to speak? I think they're going to. Okay, so I have equals AB squared minus A squared B times over A minus B times 1 over A minus 1 over B. Okay. Let's get a common denominator here. So I've got, I'll keep that delta AB for now. A minus B times B minus A over, let's see here, A, B, yeah, times AB. Okay. Oh. So that becomes minus that. So I've got A squared B minus AB squared all over AB. Okay. Pull things out. I have B minus, or A minus B. I made a mistake somewhere. I might have plugged in things into, more than likely what happened is I plugged things into my integrator incorrectly. Okay. I don't actually have a calculus book here, so I screwed things up. Because when that is all said and done, it should work out. In this case, it obviously doesn't. Okay. So, is Van Laar thermodynamically consistent? It is. But Dr. Hadley's math is not to be trusted, apparently. But you got to remember the steps here. Okay. The steps are important. I first write down my definition. Then I use log rules. Then I plug things in. Then I make all my x2s into x1s. And then I move forward to simplify everything. So, and that's where things went awry, I think, is when I actually integrated it and simplified.